Good afternoon, everybody. My name is Sava Stasu. I'm the director of the Institute of Energy Futures at Brunel University, London. It is my great pleasure to introduce our speaker for the open lecture this afternoon, Professor Maria Kolokotroni. Maria has been a colleague for many years, probably now over 20 years. Has been a Brunel for a long time. And she has been making significant contributions, both academic development and research. She is currently a professor of energy in the built environment at the university. She's a chartered engineer and a fellow of the Chartered Institute of Building Services Engineers. She's a member of the International Agency of the Air Infiltration and Ventilation Center. She's a board member of that. And she currently participates in the international project Annex 80, which is on resilient cooling for buildings. She has coordinated and participated in a large number of EU, UK, and international projects on energy efficient technologies for buildings, nearly zero energy building and ZEP retrofit, low energy cooling and ventilation systems, urban heat island, and the quantification for London and its impact on energy demand by buildings, and mitigation strategies such as cool materials and microclimate interventions, as well as the impact of climate change on the energy performance of buildings and the urban area. And now Maria's talk today is going to be on retrofitting resilient buildings to net zero energy. So Maria, over to you.
Okay, thank you very much, Savas, for this introduction. I will try now to share my screen. Thanks for the introduction, Savas. The title of my presentation is Retrofitting Residential Buildings to Net Zero Energy. And Savas talked about my credentials, so I will go to the next slide, which is about energy consumption in the UK in 2019, which is the latest data that we have. We can see in the diagram that residential buildings, domestic buildings, they consume, is the sector that consumes the second biggest energy in the UK. In many aspects, energy used by buildings has decreased in the last years, mainly due to energy efficiency measures. Residential buildings have decreased about 0.7% compared to the year before. And longer term, their energy use has decreased by 12% since 2000, despite having an increase in the number of households and increase in the population. And per household, it has fallen by 23%. Despite this reduction, final energy use was 142 million tons equivalent in 2019 in all sectors, and with domestic sector being the second most consuming, as I mentioned before. So there is scope to further reduce energy use as low as possible, using technologies and also changing behaviors of the users so that we can achieve zero or nearly zero energy use. And first, I thought of putting some definitions here. What is net zero energy buildings? What is nearly zero energy? And what is zero carbon buildings as well? First, energy is used by a building and its system to provide safe, healthy, and comfortable conditions for its users. Carbon is the amount of carbon dioxide emitted or equivalent emitted by the energy uses in the building, and the amount of the carbon depends on the fuel that it is used for the production of this delivered energy. Zero energy building is a building that does not use energy from the grid. A nearly zero energy building is a building that uses a portion of energy other similar buildings use. A zero carbon building is a building that does not emit carbon dioxide equivalent emissions because of the energy it uses. And zero energy or zero carbon is not equal to zero energy because carbon depends on the fuel used. And finally, we use sometimes primary and delivered energy, these terms, and primary energy is the energy as produced without taking into account conversion or transmission losses. And this is usually measured in tons of oil equivalent. And delivered energy is the energy as it arrives in the building minus the conversion or transmission losses. And this is the energy that usually we are build because we have used it in our building. So I talked about energy or the definitions of what a low energy building is. But why we provide this energy is in order to have a safe, as I said before, healthy and comfortable environment. And the four areas that we try to provide this comfort is visual comfort as we perceive it with our eyes, acoustical comfort as we perceive it with our ears, thermal comfort as we perceive it with our skin, and air quality as we perceive it with our nose, but also the effects that it will have on the health. So there are two aspects here. And all these conditions, they are provided by the building, the envelope and how we design it, the installations for heating, cooling, air conditioning, and also lighting and so on. And users are quite important in this aspect because they moderate how the energy is used according to their needs and according to how they want to use it. So a nearly zero energy residential building means a building with a very high energy performance. And this performance can be achieved by three methods in this pyramid. First, reduction of energy use that it is needed by using passive methods for heating and cooling, such as ventilation, and for lighting, such as day lighting. Then energy efficiency measures, energy efficient appliances and lighting, low energy systems for heating and cooling. And finally, renewable energy integrated into the building to cover the residual energy which is needed. Of course, these are, the principles, but how we reduce the energy and how we provide this energy efficiency is the big question. And we have seen in the press quite a lot of debate later. I put this headline here from BBC News about ban all gas boilers from 2025 to reach net zero. So there is quite a movement to change the fuels that we use to heat our residential building, our houses. And how we can change gas, there is quite a lot of proposals. Hydrogen is one, heat pumps is another, but there are quite a lot of ways, and the reduction of the energy, the measures to reduce the energy, it will help us also to need less for heating. The building regulations in the UK encourage net zero buildings, but because they require calculations of the CO2 emissions from the dwelling, that they should be less than a target that it is specified. Also, they encourage the fabric energy efficiency of our buildings, so insulation and measures like that, they are important. And then passive control methods, and also how we operate as users, as occupants, efficiently our houses. There was a recent consultation on the future home standard and in the building regulations. And there was a regulation 25B about nearly zero requirements for new buildings. And the consultation has proposed to keep this requirement, but simplify it by removing example systems that they were there, so it makes it more flexible, and also by removing the requirement to give notice to the local authority, which again adds to the flexibility. And the next question is, why retrofit to nearly or net zero energy? We all know that the existing building stock is not very energy efficient, and it is also responsible for quite a lot of the total energy use and carbon emissions. And this building stock will be standing for the next 30 years. So there is an opportunity for energy renovation interventions that will cause positive impacts at all levels. And apart from improving energy efficiency and reduce carbon emissions, also we tackle energy poverty, we mobilize the construction sector, and also we contribute to a cleaner, healthy, and sustainable environment. However, the energy efficient renovation of residential buildings especially has very low rates at present. So there are initiatives and policies that they are proposed there to encourage to do these interventions. But the tools and technology specifically for existing residential buildings are needed to achieve this, and these are not fully developed yet. So in retrofitting residential buildings, should energy efficiency, decarbonisation, and integration of renewables be the only consideration, which is what I mentioned before? And the simple answer is no, as they need to be considered together with affordability, so costs are very important, life cycle thinking and circularity, and how we use the systems and the materials we use, how energy efficient they are in their total life cycle, also high health and environmental standards, and addressing the digital transition as well, how we use this in our buildings. And finally, respect for aesthetics and architectural quality, because if a building is not accepted by its users and the society, then it is not going to be duplicated, it's not going to be repeated. So I will talk about a project that we started about 4 years ago, and it is near to completion now, which is about residential retrofit to create an assessment platform and demonstration for near zero energy and CO2 emissions with optimum cost, health, comfort, and environmental quality. And in general, for this project, we need to plan it in the right way. We need to carry out the interventions in the right way so that we can get it right in the end. And this project is a European project, and it involves a large number of partners across Europe. The project has got this three-step approach. First, as I mentioned before, the refurbishment assessment through a tool that we are developing, which provides a holistic overview, which includes cost, energy, users' requirements, and life cycle assessment of the renovation potential for different scenarios that they are user-driven. And then it is the planning to consider costs and consider how the intervention is going to be carried out. Do the people need to move out? Can they stay in? What we can do in order to have the buildings operational during the refurbishment, for example. And that will select an optimal action plan and optimization of the installation process. And then the renovation, the installation of the personalized technologies that they have been determined through this tool. And the 4 pillars of the interventions are, of course, energy efficiency with different technologies, cost and time efficiency by using an integrated project delivery and looking at the cost and also the synergies between the technology, the human health and comfort, as I outlined before, and also looking at ventilation and air treatment, which has become quite important, especially the last year or so. And of course, looking the environment, looking at the urban microclimate around our buildings, how this can be improved so it can reduce energy and increase comfort, the renewables, and in general, the decarbonization of the whole process. The Recost web platform is a fast, user-friendly energy retrofit analysis tool, and we rank a large set of alternative scenarios, allowing the user being the designer and the user of the building, that it is encouraged to take part in from the beginning to define the selection criteria. And the objective is to identify the renovation scenario that allows the most balanced outcome of energy saving, CO2 emission reduction, and cost optimization. And the selection is based on data, on the current condition of the building, and the number of the different scenarios that are examined, which include conventional and innovative retrofitting technologies. And then it allows to prioritize which interventions they are the most attractive according to the criteria that they have been selected. So it is a web platform that includes tools that they have been developed. They are pre-existing but developed further by the project. It can include other tools that they have been developed by others. And it consists of a structured sequence of actions. First, there are site visits and energy audits in the buildings to evaluate the current status and the energy consumption. Then the data of the building is inserted in the platform to quantify the estimated energy and emission saving potential of the different technologies. Also considering the characteristics of the building, the specific building, and also the climate. And then the various renovation scenarios are investigated and ranked according to 4 criteria: impact on energy consumption, which is what we are interested in some cases, but also cost, which will help to penetrate faster, life cycle cost, and of course improvement of indoor conditions, because there is no point in saving energy if the people they don't have comfort in their houses. And then just an example here of one of the tool, Epicure, which has got different elements of the building that they are looked at one by one, and then subdivided, and they are looked again. And all these, they are ranked in order according to costs and energy efficiency for the needs of the particular building. And finally, but not least, is that when we evaluate the package solutions that we propose for the building, then we calculate the energy, but also we calculate the financial performance of the set of packages. So we've got a financial performance, costs, we have an energy performance, energy, and then looking at what each one offers, then we can choose one scenario which is affordable, but also will deliver the most energy reduction. And in order to achieve that, as I said, we can use conventional technologies, but also we need to use new technologies that they have been developed in the last few years. So the technologies that we looked in the project, it is of course heating, ventilation and air conditioning, and how these will be installed in the building. We looked at the building envelope, insulation and the windows. We looked about how we can provide passive solutions to avoid overheating, and solar energy harvesting as well. And finally, nature-based solutions that they will help us to provide acceptable indoor air quality. We have demonstration buildings that we looked and installed these technologies, and some of the buildings were fully renovated in Denmark, in Spain, in Switzerland, and in our campus in the UK, in our Brunel campus, one of the residential buildings. So we, in our residential building, in our UK demo building, we installed the technologies as they were developed, and then we monitored their performance. And we have the technologies that they reduce heat in demand, the technologies that improve indoor air quality and thermal comfort, and then we have renewables. So I'll go one by one and show to you what it is and how it was installed in our building. First of all, vacuum insulation panels provide an attractive solution because their thermal conductivity is very low compared to more conventional insulation materials. So with much less insulation, thickness of insulation, we can provide the same protection. This is how a vacuum insulation panel looks like. And then the question is where to add this insulation, internally or externally. Externally, it is attractive because we don't have any thermal bridges, and also because then we don't take up floor space, interior floor space of the building, but it is more expensive to install because it needs protection from the elements. And interior as well, I already outlined that we can have thermal bridges, so less protection, and also it will take some of the floor space. And sometimes residential buildings are very small bedrooms and living rooms, so we don't want to lose any of the floor space. So we decided to apply it externally. And in order to install the vacuum insulation panels, they need to be protected because there is vacuum, so they need not to be pierced. So there was a system that was designed on how to do this, and this was part of the exercise. And you can see it here where it was installed and the final surface here externally as a demonstration. And this was quite nice because it created interest from our users and the students. And together with the residencies, we carried out an art competition. And this is one by the students, and this is one of the winning entries that we wanted to paint on the wall to raise awareness of this issue and renovation of residential buildings. But then the first lockdown happened last year, but we hope to do it this summer. So this probably will be materialized. And now how it performs, we can see here a thermal image of the wall, that we can see that where the panels are, it is much less hot. It's a much colder surface. And in this graph here, you can see from sensors that we have installed that there is quite protection from the external elements, and this is the external, before the external brick surface, and this has stayed quite higher than the ambient temperature, so it provides quite a few degrees of protection, so we have much less thermal heat transfer, so we have got much less heat escaping from our building. The second technology is windows, and windows, we like them. They give us daylighting and allow the view outside, and also ventilation. But sometimes we keep them closed during the winter, and it doesn't bring enough ventilation in our building for indoor air quality. And when we open it, then we lose heat. So this smart, innovative window, it uses the two panes of the glass as a channel to get air from the outside. This is then heated between these two panels, and then this is being let into the internal space. And apart from the heat recovery that it provides in terms of energy efficiency, it also, the air that comes from outside, it doesn't create drafts, so there is less chance of the occupants to block the trickle ventilation ventilators that we have seen in many occasions to be blocked in houses. And again, these diagrams, they show what happens. They also show that in the winter, we don't want the hot, in the summer, sorry, we don't want the hot air to come inside the building. So it is recirculated and goes outside, whether another trickle vent is bringing air from outside. And this window also, it's still being developed to include phase change materials in order to increase the efficiency. So it was installed in our building, looking the same way as usual windows. And also we measure the performance in one of the installed windows by installing sensor at the bottom and the top of the window. And the line that we are looking here is this red line, which is the difference between top and the lower part of the window. And we can see that the air is heated, and that was in January 2021. It was heated about 5 degrees when it comes into our space, so it comes warmer. So it seems to be working well. I will now move to the technologies to improve indoor air quality and thermal comfort. And first, the nature-based solutions. It is plants that they help to passively, although it includes a small fan, reduce the pollution inside our buildings. Particular matter and volatile organic compounds, but also relative humidity and CO2. And this is a standalone unit that can be installed, can be just put in any space. Here in the kitchen, and here in the kitchen in another building. and as I said, decreases particulate matter, VOC, and we have seen reduction of CO2 and a slight air cooling and humidification effect as well. And another development during the project, it is the same unit with plants that could be put on the place of a window, for example, and appears like a small conservatory. And the indoor air is ejected at the bottom of the unit with a fan, and then it is directed upwards, and due to a specific design is guided through the long path between the plant leaves, and then exits the conservatory unit with improved air quality parameters. And here is the installation in our building at the campus. And here we have carried out tests, and we have seen that the Areo plant, the standalone unit, has reduced the PMs 2.5 about more than 70%, the VOC about 35%, and then the Cassetta unit, again the VOC about 40%, the PMs not so much, and we think it is because it needs some improvement. I think the fan, the recirculation was too high, and also we don't have so many particulars in the corridors like that we have in the kitchen where the Areo plant was installed. I move now in another way to use phase change materials in ventilation system to improve thermal comfort. And these materials, they are encapsulated in panels to form thermal batteries within the ventilation path to store and release heat. They use the latent heat to store energy, which is charged during the night and discharged for cooling during the day. So we have the PCM. As the temperature rises during the day, it becomes liquid, and this the heat that it is, or the coolth that it is coming from there, it is carried through the air to our building, and then during the night it solidifies again, and then the cycle starts again. Such a unit we have again installed at Brunel, at the top flat of the building, and the PCM materials, the thermal batteries here, and in the corridor we have the air supply and extract of the air. The system is very simple. It is a fan, and then we've got the PCM batteries here. We have a bypass damper to bypass the PCM when we don't need to condition the air, but when we need to condition it according to the sensor in the condition space, then it goes in there to cool the air from outside. And then we have the return air, and again a recirculation unit that if the conditions of CO2 and relative humidity are okay, then some of the air can be into the building again. So here is the graph of how the building, the system performs. And I think the important lines here is this light blue line, which is the room temperature, the corridor temperature, with a set point of 22 degrees, and we are trying to keep it at that temperature during the day. So what happens during the night? The PCM gets solidified and the temperature drops, and then during the day, when the external temperature is below the set point at 22, the thermal batteries are bypassed, and as long as it goes above 22, then it goes through the PCM, and we can see it working here, and then it provides air into the building that keeps the temperature at that temperature of the set point temperature. And at the end of the day, when the system was switched off, we can see how much higher the temperature inside the building is. And we carried out quite a few simulations about what is the thermal comfort that provides into the building. And we can see without the system, the dot lines is hourly values of what is the temperature during the months from April until September. And we can see here is what we are trying to achieve in our building for thermal comfort, or an upper band, and we can see that it is not comfortable. But with the system, we can see again that most of the hours, they are at the thermal comfort range, but at some cases which have some overcooling, so it needs to be a little bit more fine-tune the system to avoid this overcooling. The cool roof materials, cool materials, reflective materials, they are quite passive methods that it helps us to avoid overheating in our buildings. They are materials that they have got high solar reflectance, high infrared emittance, so less solar radiation is absorbed, and there is a faster release of heat during the night. So we have lower external temperature, which allows less heat to penetrate into the building, less heat transfer, and then less heat is transferred to the ambient air. And here you can see a diagram of that. Less radiation is reflected over a normal typical roof, while with cool roof, cool paint, cool membrane, a higher percentage is reflected, so we have a cooler surface. And again, we applied this in the roof, and actually it is an experiment, so we applied it to half the roof and the other is for us to compare. But again, this was done just after the first lockdown last year, and then it was not possible to install sensors, but now they are installed, so we will measure the performance this summer. But here I'm showing a graph of intervention that we did at Brunel some years ago in another building, where we can see the 2 days that I have selected here with the same solar radiation externally and the same temperature externally, ambient air temperature. We can see that the surface of the temperature of the surface of the roof is much less after the application of the cool membrane. And of course, the internal ceiling temperature, again, it is much less, which contributes to less overheating, improved thermal comfort for the users there. And finally, but not least, about renewables. And concentrating photovoltaics is the technology that has been developed in the project. Also, commercially available PV panels were fitted on the roof of the building. And the concentrating photovoltaics have been designed, manufactured, and tested at Brunel by Dr. Harjit Singh and his team. And these CPV modules maximize the availability of solar radiation, and they improve the electrical conversion efficiency of the solar PV cells, and also the target in the beginning to produce 10 to 20% higher electricity, lower footprint by 40%, and lower cost, and the electricity has been even more, as we will see in a little while. So the increase of the electrical energy generated per square meter of available roof space make this system quite attractive and convenient in buildings because we have so much roof space or floor space. So the more efficient they are, the more power they generate, the more of the energy needs of the household they are going to provide. So these are the different, the developed design, taking into account local weather and solar climate. COMSOL ray optics were used to simulate and develop the system. Compound parabolic concentrating optics based were developed, and also up to 40% more power is predicted to be produced by the CPV panels based on the cell area. And in reality, this happened. Here we can see the installation at Brunel, the 3 different types that they were installed, and also the installation at a switch building at the V, again, to be evaluated at the different climatic conditions. And the measured performance is here. Over the summer of last year, actually over 7 months, we can see the measured energy output per square meter of the flat commercial PV panels, and you can see the different designs that they produce much more with the ACPC variation design to have almost 40% more of the output. So what does it mean, all these technologies, for the energy use reduction? So we carried out quite a lot of simulations for the Brunel building, and we can see here before the interventions, the heating, electricity, domestic hot water and cooking, the energy consumption by the building. And we can see what the different technologies can provide. System, the heating is quite important, energy efficient boilers or other fuels and methods, but in our case, it was gas boilers that we simulated. Our vacuum insulation panels, they can provide quite a bit of reduction, and the windows as well. And here I have the air tightness, which is to make the building as tight as possible so that we can avoid unintentional heat losses due to ventilation. And this is regulated by the regulation, building regulation, so it needs to be done anyway. In terms of the cool roof, we improve the overheating conditions, the comfort conditions in the building, but there is a penalty because it reflects solar radiation during the winter as well. So there is a heating penalty, but it is very small. And finally, the PV and CPV production. The CPV, as we measured and as we can see here, can produce more power, which can be used to offset some of the electricity that it is needed in the building. And we have been talking about the future, and these buildings are going to be standing there for at least 30 years or even more. So we looked at how the different technologies will perform in the future, 2050. And then you can see that because ambient temperatures will rise, then in terms of heating, we have a beneficial effect. Even if the buildings, nothing happens in the building, then we will have a reduction in energy use. But the different technologies, air tightness, VIP, windows, the cool membranes, they are all perform well, perform the way that we expect, and the same for the PVs and CPVs. And here, because solar radiation will change in the future, there was what will happen, and we can see here that we have got a little bit of reduction, but not a lot. So there are no peculiarities with any of the technologies, but the summer overheating has not been analyzed yet. So we need to look at that to see how much our building will overheat and how much cooling we need to provide in the building in order to keep thermal comfort without needing to install air conditioners. And with this, I think I will finish. Thank you for listening. And here is the team at Brunel that they have been involved in this project. Harjit Singh, Ranga Vihari, Agnese Salvati, Jose Tavares, and Brunel Estates, that they were very helpful, and actually the success of the project is owed to them, and also Brunel Residencies. And here is the website of the project if you would like to follow some other developments for other countries as well. So thank you very much.
Thank you, Maria, for the interesting and very clear presentation. So I think we start with questions and in the question box, and I think the first one we have that has been there from the beginning is the definition of the net zero. What does it really mean? I think you tried to answer it at the beginning, but perhaps you can sort of go
answer it again. Yes, thank you. I mean, this is a very important, a very important question. I tried to define what net zero energy means, which is that our building is self-sufficient, so it doesn't need any power from the grid. That means it consumes energy which is produced by the building. But maybe the question is not only about that, but it is about the life cycle net zero. So how perhaps our the materials that we use of the buildings, the embodied energy of these materials, how much energy we need in order to produce these innovative technologies, that they might be more expensive in terms of energy to be produced by more conventional technology. So this is something that hasn't come to the definition that we only look about energy, but I think it is coming slowly, in the same way that 10 years ago we were talking about nearly zero energy buildings without looking at environmental conditions. But now we don't. We have to provide the requirements in the building with as little energy as possible. So I think that this is how we can define it. And the nearly term, again, there are different definitions, and it depends on which country you are, because they are defined that they are buildings that they require a portion of the energy that similar buildings are required, and so it depends on which climatic region you are.
You move on to the second question. Is from Joe Cottrell. It's about the cost of the strategies that you have implemented in the building. So if you have any idea about this cost, the cost per square meter?
Well, no, at the moment I don't have any idea of cost per square meter, because in many cases they were a first installation of an innovative system. For example, the VIP panels, they needed quite a lot of work for the design and the installation and so on, and the same with the nature-based solutions as well. So the answer is I don't know now. but I will probably know in about a year's time when we do some calculations of the developed technologies without having to develop them further, how much they will cost in order to install them. So sorry, I don't have an answer to this question.
Okay, and the following question is from Stefan Simons, and is about the skills required for the installation of these technologies. I'm not sure whether you can see the questions.
The question is, we are told that we don't have people with the right skills in the UK to carry out such retrofitting. Do the technologies you testing require any special skills for installation? The answer is yes. We do have skills in the UK for some of them, and actually some of the systems that we installed, they were manufactured in the UK, but some others, for example, the VIP panels, we had quite a lot of difficulty in finding installers in the UK. The panels were produced by a manufacturer in Germany, and then they came here, and then it was very difficult to find somebody that we could install it, and also take into account or you know, the fire protection, the health, and everything, to have the complete package. So in our case, we have design it, so we are creating the skills, and actually between ourselves we were joking and say that we will establish a company in the near future because we know how to do it. And also the other bit is the nature-based technology. Again, it is something that it was developed in Austria, so we had to install it by them. But again, it is something that we now know how to do it, and the skills probably they can be in the construction sector in the UK. So it is, the answer is yes and no. We do have some skills for some of the technologies, but we are lacking some, and this is something that we need to work on.
Yeah, we have another question from Joe Cottrell, Maria, about the cost, sustainable costs for the retrofits. I think you tried to answer that question, but it's whether really there is a definition of sustainable costs. In terms of
what do you think a sustainable cost point for this? Well, a sustainable cost point would be, again, I do not want to put it in pounds per square meter or something like that, because it probably is very premature. But I will put it in a different way. In many houses in the UK, we change the windows every, I don't know, 20 years or so. And there are quite a lot of buildings that still they have very, very old windows. So to install energy efficient windows according with the building regulations, then they will cost an amount of money per square meter. If, when this installation is going to happen, if we have an innovative window that we can install, that it is the same aesthetically and easy to use by the user as the one that was going to be installed, but costs, let's say, 5% more than the more typical window, then we will need to only have into mind this 5% of additional costs. So this is how the least cost methods come. So we look at when different interventions, what it needs to be done in the building, when, and then rather than doing them all together, we can do them when they are needed, or when one of the elements was to be replaced, so that the total cost is just a little bit more than a typical retrofit.
Okay, thank you. I hope that answers the question. Now we have another question in the chat box, and it's from Sebastian Wang. And it says, based on your current project experience, what would be the biggest challenges you can predict for deep building retrofit, maybe technically and from policy perspectives in the UK?
Yeah, there are quite a lot. I mean, when we do a deep energy retrofit of the building, then there are technical challenges, but then the challenges are can be solved because the technologies exist. There is a link here to the cost. I mean, they can be solved, but at what cost? And this is the question. At some stage, it might need that we need to have a policies. We have a lot of policies, but a policy on what we would like to achieve and how to achieve this, and probably create incentives that they stay there for a long time, so that an intervention can mature and then it can be applied more and more in the building. So the challenge to my mind is how we can do it in existing buildings, taking into account that they are operational buildings, and how we can persuade the owners of these buildings and the tenants of these buildings to carry out these technical energy efficient solutions that we have. And also it depends what we want to install and how. For example, in the Swiss demo building, there was a developer that was carrying out the retrofit, and then they decided to go down to the photovoltaics, so to create as much as energy from the photovoltaics, and this has been very, very successful. And also at the same time, they added 2 floors in the building, so there was more floor area, and these 2 buildings, they were less costly to install. So we need to look, I mean, what private developers are looking for, which is maximum money for their investment, but also if we are talking about not developers, but private individuals with a house, what incentives they might have in order to install these technologies.
Thank you. And there is a question from Marjorie Bahaj.
We're spending a lot of time and energy adapting existing buildings often of poor quality. Do we need to think about completely built on town and cities to be energy and carbon efficient, as the climate change and crisis is becoming very scary for our one planet home existence? Very nice, very nice. Yes, it's a very good question. If I take a back seat, I would agree completely that if we start from scratch, then we build our buildings with the technologies and then thinking of today. And I do agree that some of the buildings, they are of not so good quality. But if we are thinking about cities and towns, it is very difficult to demolish big areas and build from the beginning. We can develop new areas outside the towns and cities, but still they will exist, and we keep them for years to years. There were some experiments in Europe, I think, and also in the UK, in trying to start from scratch in existing areas. but it needs a lot of effort. It needs a lot of the will of the city dwellers and the people that they live there. So we need to find ways of improving our existing buildings. They will stay here, and the easier we make it because of technologies, policies and incentives to do this upgrading or deep retrofit. It depends. Sometimes it's upgrading, sometimes it is more deep. Then we will have to live with it. So my answer is that if the cities were developed with what we know now, we would have done it differently. But they are here, and it will be very difficult to demolish and rebuild them. So as I said before, I'm repeating myself now, is we need to find a way to make them more efficient and provide the health and comfort that the occupants are used to.
But I think, Maria, just a comment from me really here is that it's about the character of the new buildings. And I think from my experience, really new developments probably, in terms of character, really, they don't compare very well with sort of buildings that were built probably, I don't know, 40, 50, 100 years ago.
100 years ago, yeah.
And I think that's a big issue, really. I think for probably a lot of the large portion of the population, if you give them the choice of where do they want to live, it would be interesting to see what happens.
Yeah, that is an interesting question, and of course, a lot of people they like to live in you know, city centers and buildings with the character. So as I said in the beginning, the aesthetics and the acceptability of the building form is very important. If it is not acceptable and it is not liked by the people that they are going to live there or buy it, then it will never catch up. It will never be replicated.
Yeah, and another question from me is about the compromise between the energy demand reduction for heating and also the ventilation requirements. And ventilation requirements not only about sort of in terms of thermal comfort, but also in terms of, for example, the issues of COVID and so on. So how do we balance that, particularly with the new sort of revisions to the building regulations? So I was wondering how they would try and balance those conflicting sort of requirements. The new regulations or the revised regulations, so I don't know the details, but I think for me it's quite sort of an interesting problem.
It is an interesting problem. I mean, at the moment, not in the building regulations, but the various guidelines that professional institutes they are given because of the COVID crisis is, of course, to increase ventilation as much as possible. But of course, this has got a big energy impact on the heating. That is on the energy that is needed for heating. The thing is that if our buildings are ventilated with the right amounts of fresh air, outside air, in order to keep the usual pollutants low, and then if we have rapid ventilation means like opening windows, for example, when there is a need, we have a particular event of pollutants, then this is how ventilation and heating and cooling demand they can be met at the same time. So it depends. I mean, what is the indoor air quality that we need to provide? And of course, the different pollutants like VOCs and it is not only CO2, it is humidity and other things in our houses that they need to be taken into account with increased ventilation and with rapid ventilation, a lot of air from outside for particular events. So it is an interesting area. I mean, how you balance it and how much energy you need to use to heat this air is important. But this there are ways, this smart window that I showed, then it can provide some heat recovery and it can provide more ventilation with a temperature that we can accept. So we get the indoor air quality effects of the enhanced ventilation without the energy penalty.
Great, thanks very much, Maria. Thanks very much to everybody attending and for the questions. Great.
Yeah, thank you very much for listening. Thanks for everything.